Okay. So, gave you a little time to work on this. Seems like you're doing okay. You get dy dt equals r times the square root of 20y. That rearranges to dy over the square root of y equals square root of 20r dt. And what's the antiderivative of the square root of y? Well, it's going to be a square root of y. But if you take the derivative of the square root of y, you get 1 over 2 square root of y. So you're going to have a 2 here. And over here, you just get your integral, which is very simple, right? So, put the integral sign here. Skip the step where I do the rearrangement, because it's all kind of implicit. So you got 2 square root of y equals this, so the square root of y equals, well, it's going to be the square root of 5rt. Let's see. Okay. Now there's square root of 20 over 2 is square root of 20 over the square root of 4, which is square root of 20 over 4. And I shouldn't have to say that, but I know I do sometimes. Okay? You got to get that rust out. But then you square this. Okay? And there we have it. So this is going to be this. Okay? Now, if the area ratio, let's see, I think for that bottle, wherever I put it, keeps running away from me, diameter of the cylinder is about 10 centimeters. The diameter of the tube is about 0.3 centimeters. Okay, assuming that, we find that it takes 100 and some seconds for the water to all flow out. Okay, so I can kind of check the solution, see if I actually set the thing up right by taking some data. I'm not sure about that ratio, but that would say that the area, or the diameter of the cylinder is roughly 30 times the diameter of the tube. So your area ratio would be the square of that, 900. So R would be 900. Y of 0 is, let's say, 0.15 meters. You get an R squared there. Make that coefficient really tiny. And that's just not going to work. In the first place, R is supposed to be the area of the tube over the area of the cylinder, so it should be like 1 over 900. So 5R squared would be like 5 10,000s. That would be worse than that. It would be like 5 millions. Okay? It's way too small. So something's wrong here with my model, with my reasoning here. We got 30 tubes across that. And I forgot, yeah, I've got the square root of 20 in there, so I got the 5. Yeah, something's terribly wrong, but this is how it would work out. It does not work out the way it should. And of course, I'm doing this off the top of my head, because I didn't know what we were going to do today, because I didn't know what homework we'd have done. Okay, so if R is 1 over 900, y of 0 equals 0.15 meters, you get first of all, y equals approximately 0.0000006 t squared plus 2 times the square root of 5 is roughly 4.5, a little over 4, times c times r, so that would be 4 that would be this. And then y of 0 equals 0.15 square root of 0.15 is pretty close to 0.4. So we would end up with something like y equals this plus 0.002t plus 0.15. Now, there are two things that disturb me there. I've messed up the model somehow. Wait a minute. Okay. C could be plus or minus because we're solving c squared equals, right? So this would be a plus or minus here. And this has to be negative. Now, if I divide this by this, I get something in the order of 1,000. And then divide by twice that, I get something in the order of 500. So it should take 500 seconds if I've got my area ratio right. So that's probably wrong. Okay? So it's the area ratio that I think is a culprit there. It takes about 1/3 that long. Okay. So anyhow, first of all, I want you to see that this model comes from something that's very easy to understand in the real world if you know a little bit of physics. Okay? Halfway through the first semester, you know enough physics to understand this. Although we have to define pressure, it can be done in a way that we can do it before we do fluid mechanics. Okay? I'm quoting Bernoulli's equation. Well, it's a consequence of conservation of energy. And that's what this is, and so forth. So you don't need to know where this comes from. Just know that it comes from someplace that's not too deep. It's the way things act. Okay? You get this equation, which is very easy to solve, and come to this conclusion. Okay? So I'm probably, for homework, I'm probably going to take some careful measurements. Ask you to double check my solution here. It's pretty straightforward, but you never know. Okay? And see if you get a model that predicts that this thing is going to reach 0 at some other point. Okay? At some other time. Okay, good. So, let's look at an example from the text.